In this video, I will explain you what is the total energy stored in a capacitor. Now, before that, you should know how a capacitor has been made. Then you will come to know how a capacitor can store energy. Now, in a capacitor, let's say we have two plates. I am going to give one positive charge. Okay. Now, to do first positive charge, I don't have to do any work because there is no electric field here. Now, for next positive charge, I have to do work because this will be repelling. So, I have to apply a force and displace it to here. Force is W1, let's say. Now, I am going to add one more charge. So, but here in this case, for adding third charge, these two will be repelling. So, it is higher amount of work, right? So, that is comparatively higher work. So, I am going to mark it as in bigger W for third charge. Now, to bring fourth charge, I have to do more work, right? Because there are three charges repelling me. So, higher work. Now, this will keep on going in this way till the last charge has been stored into the capacitor. Now, this process, we know the works are different in between different point at the charging. For the second charge to store work done, let's say if it is W, for 99 or 100 charge to store, it will be a higher amount of work done as compared to the second charge to get stored in the capacitor. Now, to charge the capacitor right away from 0 all the way till Q, the total work done is nothing but the energy stored. That is the work energy principle. Whatever the work we are doing, that will be converted as the energy, right? Energy can neither be created nor be destroyed. Now, so why I have explained you in this way, we have to do integration here as work at different positions are different. If at all, if it is the same work, then I can simply multiply this. For example, W plus W plus W, it will be 4W. But I can't multiply this as 5W here because the works are different. So I have to integrate. Now, what is the equation for work done? So energy stored is nothing but work done. Energy stored U is nothing but work done. We have one equation for work done, that is QTV. Now, we are storing it from 0 potential all the way to the full potential. Clear? Now, 0 to V, we are doing charging, and that is when the capacitor is fully charged. So, 0 to V, we are adding all QdV values. Clear? Now, for Q, I can't integrate in this way because see, the integrating parameter is dV and I don't have V here. So, I have to bring V here. How can I bring V here? We know Q is equal to CV. So, substitute CV here. So, this will be 0 to V. Q is nothing but CV into dV. Clear? Now, I can take the common constant outside. C, 0 to V, V dV. Now, C, what is integral of V? Increase the power by 1 divided with the same value. So, integral of this is V, this is V power 1. 1 plus 1 is 2 divided by 2. And what are the limits? 0 to V. Again, take the constant out. That is 1 by 2 into C. Put the limits. This is V square minus 0 square. And that will be half CV square. And half CV square is the energy stored in a capacitor. You can have two more equations. Half CV square is the equation, now we have got it, right? I can substitute Q as CV. So, just substitute for C as C, I am going to substitute as Q by V in this equation. So, this will be half Q by V into V square. What is that? Half QV. Clear? Now, one more equation you have. Instead of V, you can substitute Q by C. So, from here, I can get V as Q by C. Substitute it here. So, half into C into Q by C, the whole square will be Q square by C square. So, C will cancel and this will be half Q square by C. So, Q square by 2C. So, this is an equation. Q square by 2C is an equation, and half CV square is a very important equation, and half QV. These three are equations to get the total energy stored in a capacitor. And one more thing, very important thing, whenever we are charging a capacitor, how much energy has been lost. So what is charging of a capacitor? Charging of a capacitor is nothing but, see, I am going to connect it with a battery. So here I have got the total energy stored as half CV square and Q into V by 2 and Q square by 2C. Now see, let's say this battery is going to send a charge of Q here, right? Now what is the total energy this Q is having when it is just, when these charges are inside the battery? We know, see, these charges, from where it has came? From battery it has came, right, while charging. Now when the charges, Q amount of charges are very near to battery, what is the total energy? We know the total energy is nothing but work done, or energy. We know the equation for potential energy. What is the value? Q into V. Now the total energy at this position, it was Q into V. Now the moment it is being stored in this capacitor, this has become half QV. See, here it is full QV, 1 QV, but here it is half QV. What is the energy lost? Half QV has been lost. Now, is that a problem with law of conservation of energy? No. See, from QV, only half QV is stored. What has happened to half QV? That has dissipated as heat. So this is nothing but heat dissipation while charging. So the efficiency here, or you can say that if you are providing 100 joules, only 50 joules will be stored in a capacitor. Okay, now the remaining 50 joules will be lost to surroundings as heat while charging. So it is not a good idea to store the energy from a battery to a capacitor, because half of the energy will be lost. Okay, keep that concept done. Thank you.